Okay, good afternoon. So let's get started. So let me share my screen. So yesterday, so yeah, yesterday we were looking at linear regression. So I'm not hearing any voices. Everybody's here, right? Can you hear me well?
Yes, sir.
Yes, sir.
Yes, sir.
Okay,
Yes,
okay.
sir.
Yeah. All right, thanks. So you have, yeah, yesterday we studied linear regression, and the goal of linear regression was pretty simple. So what you have is you want to learn some y which is in R. It can also be 0, 1, like it can be a classification problem as well. Nothing prevents it from you from using it. Okay, and what we said is that we would like, so your data set is given to you, xi yi I from 1 to n. This is your data set. What we said is let us try to approximate y's as a linear function of x. So we said for a w we can define the cost as follows. So we said this, right? So and then we try to minimize this, and we get like some performance, and that is what we said. But one important point, right? So let me just show you one example, and then I will try to bring this point. This point we are going to discuss at length. Okay, so you have this line. So this is the actual underlying ground truth hypothesis. But what happens is there is some kind of a noise, right? So when you actually see points, you may actually see sometimes points which are like this. Okay, so by chance you will see points which are like this, and then when you actually learn your hypothesis, you will get something like this. It's pretty, yeah. Okay, so this is the hypothesis that you will end up learning. So this is learnt from data. Okay, and this is what the other one is what we wanted. So it's a easy question, but let me just ask you, uh, what is the problem? Why is this happening?
Imperfections in the data type. Data will
Yes. So
filter and
imperfection, yeah, imperfection in data is true, but that is always the case, right? So I mean, I agree it is imperfection in data, but I want you to think more critically and say where is the problem because of which it is happening.
Sir, the training data is does not align to the like
The actual data, right?
yeah
Okay,
yeah.
okay, okay. So let me. Both of you have told correct answers, but I was kind of expecting you to tell the entire subject on your own. So I guess that's not fair. But what I'm saying is as follows, right? So you have to think of this from probabilistic standpoint. Okay, so you have some learning problem. Okay, and from the learning problem you are getting features of this. Okay, for example, if you are learning about house prices in Mumbai, right, versus let's say Goa, so surely everybody understands that the features that you get in Mumbai, the features of houses that you get in Mumbai versus the features of houses that you get in Goa are vastly different. Yes, can someone tell me in what way it could be different?
area.
In Mumbai, the size of the houses will be much smaller than Goa.
Yes, size will be
Number
smaller.
and
Number of
Yes,
instead,
floors.
number of
no,
floors.
in Mumbai it will be
Location.
high rises.
Yeah,
Yeah,
location. Yes. Yeah, Siddhant, anything you want to add besides?
yeah. In Mumbai there will be much more high rises compared to Goa. Goa will have much more villas and stuff.
Yes, yes, yes. So what we are saying is that your features, the way the features are arranging themselves, that will be different, and also for a particular feature, the prices will also be vastly different, right? So these are the two ways in which your data set comes. So your data is when you draw data set, you are drawing from some set of features that are very particular to the area that you are interested in, such as Mumbai or Goa. And given that those features are there, the prices also will be considerably different. Okay. So what is it that I'm trying to say is that once you learn a model for Goa, okay, the same model will not work for Mumbai. Okay, these models will be completely different. So your W that works well in Mumbai may not work well in Goa. Okay, so that is one issue. So essentially the problem is we are looking at, we should be, instead of trying to do this, what we should do in order to solve this problem correctly is we should be trying to find out that W which is going to be argmin, okay, argmin over expectation W transpose X minus Y square. Okay, so what I should be looking at is I should look at this quantity instead of this quantity. Okay, so uh, so what is how does what is the comparison between this and this? How do you understand? Is it similar? Okay,
Yes.
yeah, they are similar, but the only thing is this you are doing by samples, this you are doing by actual distribution, you are sitting and actually computing this. Okay, so this will be more accurate. So this is the best you can get. So this is what we should have looked for, but what we are getting is only this. Okay, so what is the thing? So this is called as empirical risk. Okay, empirical risk, and this is called as true risk. Okay, of course I have called it as a loss. Okay, so that is another name, or you can call it as empirical risk, or you can call it as data error. Okay, and so on. So now those two who were those who were saying about these 2 points, but can you now understand what I was trying to say? Was it
Yes.
Divyansh? Yeah, no, Advay, yeah. So now you understand, right? So there is a difference between saying that noise is imperfect versus saying that we are only approximating what we wanted, we are not actually doing what we should have done, right?
Yes.
Yeah, but this we cannot do, right? We don't have, if we have access to this, okay, if we actually knew this distribution, then we will not even use linear regression. Okay, so I will tell you what we will use if we had access to this distribution, but since we don't know this distribution well enough, we are only doing data error. Okay, so this is an important point, so I would like to pause here and see in the chat if you are clear so far. Yes, can you say if it's clear? You can say yes or something.
Sir, what if like we don't have those probability distributions, and still we don't want to use that empirical laws?
Hmm.
So in that case, what should we do?
Yeah, so see what happens is whenever you are given a learning problem, essentially, see, you have to understand this way. Whenever you are given a learning problem, there is some underlying pattern which you try to identify, right? See, any problem that you take, even credit default or house prices, cancer type of problems, all of this, there is some pattern that you are hoping to learn. Okay, and there are only two ways in which you can address this problem. One is you should be having the expertise to code up like exactly this thing, right? You should be able to like how visually we are able to do, you should be able to do. Secondly is via data. Okay, so machine learning is looking at approach via data, what is it that we can do. Okay, so in some sense what I'm trying to tell you is that this is because the data is the only way you can do, this is the only thing that we can do, there is nothing more we can do here.
Okay, sir.
Siddhant, yeah.
But I actually didn't get it. So, like, I want to know, like, the you are proposing that instead of using the cost function that we derived, this half summation of wtx minus yi whole square,
Mm.
we'll instead use this thing, that w star equal to argument of expectation, like this thing.
Yeah, I'm not saying we are going to use. What I'm saying is this is what we wanted to do really, right? See, given your entire data set, if I am saying that can we learn a linear thing which minimizes this loss for the entire data pattern, I mean for the entire Mumbai, I would like to compute this and find out the best W, right? That is what we have to do. But what we are doing is, it's like this is a simulation for this quantity, right? If I take n tends to infinity, it will get closer to this. Siddhant,
Mm,
if I take more and more samples, it will become closer to this. Of course there will be some n by 2 or something that may come in, but besides the constant, it is the solution of this will approach the solution of this as n tends to infinity, correct?
yes, sir.
So now because we have only finite samples, we can only minimize the loss like this. So for example, this line that we got was learned from data. The red line is what is learned from the data from the finite point. So there is some noise that is coming in because we only can minimize empirical risk or loss or data error. But what we wanted to do is over entire pattern, like all, if you could see all the points, what is it that we could have done is what we wanted, right?
Sir, for the first part,
Hmm.
I can see, okay, that the yi were the actual value, and this thing, this w transpose xi are the values which I am predicting. I'm
Yes,
taking their difference and I'm trying to minimize that thing.
yes. So
In the
this is
second, I'm unable to visualize what. So this is the variance, right?
no. So this is what I'm saying. The second part is like this is the true line that is there. Suppose there is like if you could access infinitely many points, this is the line that we would have got, right? So this is like the best line that can capture given the entire data set. If you give infinite points, this is the line I would have learned. But this another way of saying that is I am trying to minimize over expectation of this difference. So when I take expectation, I am taking the entire omega, no? Expectation is taken over the entire space, right?
Oh, okay. So we are also accounting for everything here also.
Yeah, here we will account for everything including these 4 points. And this will be the minimizer. So this is what we would have wanted. But because we have only finite points, this is what we got.
Okay, sir.
See, this is like, I will do a coin toss, okay? It gives me five times I will toss, every time it comes heads. And looking at the data, you will predict that, okay, the bias of the coin is 1, right? But that is like your empirical estimation. But I will go back and I will do the physics. I will create a proper theory as to what is the probability of getting in head, and I will say the actual thing is 0.5, right? So that is the difference which I am trying to say. You could only do it from just finite points. I could do it from my knowledge about this distribution, studying this coin. Can you see the difference?
Yes, sir. I get it.
So yeah, so basically this is susceptible to noise, whereas this is not, because we have taken expectation and all the noise goes away. Okay,
Yes, sir.
all right.
Sir, is this one of those instances where that uh, Bayesian versus frequency,
Frequentist, Bayesian versus
yeah,
frequentist, yeah. So here yeah, that we will discuss today again. We will talk about that, how that can help the problem. We will come to that, so what you are asking, but right now I am just not yet there, so we will come to that soon. I am going there, but yeah, anyway, that's a good point. It is coming towards that. So here is what we have. So uh, I'm going to state a result, and I will ask you to go back and check this yourself. It is there in my last year's lectures, but again, because I don't want to spend too much time doing algebra, this is a homework for you. Okay. So let us say uh, I will look at this this true risk, right? So I want to minimize f of x minus y whole squared over both x and y. I want to do this. Okay, so where yeah, so let me just write here where f of x is any function of x. Okay, so for a particular hypothesis I can find out what is the error, right? This is like the true risk of any function. Siddhant, this is okay, right, what I'm writing here?
Yes, sir.
Okay, so what we can actually do is we can show this risk, okay, this error will be more than or equal to okay, so this you can do some algebra and prove it. Okay, so so what are we trying to say? We are trying to say that if you knew what is the actual distribution, you can directly compute this quantity, and this is your best regression model. Are you able to appreciate the consequence of this theorem?
Yes.
Yeah, so what we are saying is if you knew the actual distribution, forget about getting data, you just compute expected value of y given x, and that's it. And that will be the best approximation for y whenever we are using least mean square loss. Okay. So okay, so this is an homework you can check for you. Okay, so I don't know if you are understanding this. There's a lot of silence here. Can I just quickly check in the chat? Tushar, are you understanding what I'm saying here?
Yes, sir, a little bit.
No, what is the confusion? Let's just have a discussion with you and me. Tell me what is the problem. Which aspect are you having confusion over? Is this okay, Tushar? What this is?
Yes, sir, that is okay. Yeah.
And you understand the difference between the data error and the true risk, Tushar?
No, sir, I have confusion about it.
So see, basically this is saying that for the given data samples, this is what we could have done. What this is saying is if we looked at all the samples and all the points, I will take an expectation and try to minimize. This is the best I can get, is what I'm saying here. For the linear hypothesis class, this W star is the best. Is that okay?
Sir, like in the above JW also, we are considering all the points, sample
No,
points.
no, only n points that you have got. That is just a representation, right? It is not infinite number of points. It's just a representation.
But sir,
Tushar.
still it is, yes, sir. But sir, still it is like it is a summation over all the data points which we are given.
Yeah. So if I give you 10 data points versus 1,000 data points, which one will you like?
1,000
Why 1,000?
means that will be like better to train. Something.
Yeah. So because it will cancel out the noises, right? So instead of 1,000, if I give you million, which is better? Million is better,
Million.
right? And if I
Yes.
give you infinite, all the points, everything I give you, which is better? Like that. That is what I'm saying. This is what we should be doing. The expectation is what we should be doing. What we are forced to do is data error minimization.
Okay, sir.
You
Now
got
I
it?
got it. Yes, sir.
Okay.
Now it's clear.
Now what I'm saying next, again Tushar, please be online. This is a useful discussion. So instead of taking linear hypothesis, why did we take linear? Tell me. Why did we take, let's say, cost function?
So we use cost function just to like measure
No,
the
I mean,
efficiency.
no, we didn't take cost function because it's too complicated. Linear is very simple. That's why we took linear,
Yes.
right? So let us say instead of taking linear, if I had taken some function, any function of x, right? This is like given any function of x, what is the best loss you could have got, right? This is that same quantity. If we didn't have the restriction on linear, but if I have allowed for any function, what is the loss I would have got? This is the left hand side. Do you understand this quantity?
Yes, sir. Yeah.
And what we are saying is, no, even if that is the case, it would have been beaten by this quantity. So here,
Okay, sir.
so what is expected? So do you understand that expected value of y given x is a function of x? Do you understand that, Tushar? I'm asking
Yes,
you
sir.
because you are a sport and you will answer questions if I pull you. But do you understand this?
Yes, sir.
So what we are saying is that this function is the best function, best model that you can hope to learn for the regression problem. That's all we are saying so far. Okay.
Okay, sir.
Now it's clear to you.
Yes, sir.
How about the others? I mean, I just took Tushar as an example. I won't pull you if you say no, but is it clear? Yes.
Excuse me, sir.
Yeah, Rishabh.
Sir, I have the doubt that yeah, as the Tushar asked that you told that if we take the large data point, that will be signify second point, but n will be the fixed for the given data set, na?
For the given data set, this n is fixed, correct?
So, so how the that first and second both are different.
No, no. So this is, see, why are we focusing on the given data set? Suppose if we didn't have, so given data set is just representing as approximation to this distribution, right? Do you understand that? So drawing these d points is an approximation to this underlying distribution, correct?
Yes, sir.
So if I had directly access to this distribution, I don't even need to use these endpoints. See, I am telling you that the bias of the coin is half. Now, do you need to do coin tosses?
No, sir.
So that is essentially what I'm saying. So when you know the distribution, this is what we would have done. If we knew the distribution, the best line to approximate y is this, right?
Okay, sir.
Sir,
Okay.
if we know the distribution, then why are we even bothering to do all this linear regression? We'll just use the distribution instead.
No, no. So okay. So the whole point is this. Okay. Let me make it very clear. What I'm trying to say is that when you learn from n points, there is always going to be error. Okay. What we want to know is the difference between the true risk and empirical risk has to be reduced. See, overall goal. This is the whole key point, right? We need to reduce this data error minus empirical risk, data error minus true risk has to be minimized. Do you agree?
Sir, can you just iterate the definition of true risk? I just went off in the whole discussion now.
Yeah, so true risk is this the actual, see, what we are supposed to do is we should try to minimize the error between the expected error between the what you are going to learn minus y, not just on the finite points, but you have to look at the entire data set, the entire omega, and look at this error, right, and try to minimize that.
Okay, sir.
Okay, so see, even though we don't know what is the underlying distribution, we can theoretically think that there has to be some distribution, right? See, if there is no distribution, machine learning itself doesn't make sense. Do you agree, Siddhant?
Yeah, totally. Yes, sir.
Yeah, so that is what we are saying. So suppose there was access to this would have been what we should have done, but unfortunately we don't have access to this. So we are only looking at finite number of points and learning our thing. Hopefully we are able to minimize this at some point, right? This is the goal of statistical learning theory, which we will get to after the midterm. Okay.
Yes, sir.
So far, any other questions you have?
So, up till now, this thing that we are saying, this ideal thing, this W star,
Hmm.
right?
Hmm.
This we don't have in our hands. This exists, but we don't have it in our hands, right?
Exactly. We don't have it in our hands. Precisely. Right.
So in
Okay.
practice, we'll still use the cost function, that half
Yes, yes,
summation.
yes, yes. We will still use the cost function. What was the point of bringing that is that if you knew the true so this is so Siddhant, W star, do you agree, is the best in the linear bag? In the linear hypothesis, this is the best
Yes.
linear, right, hypothesis. You agree with this, right?
Yes.
So now what I'm saying is, forget about linear, you take any function you want. Okay, I'm saying expected value of y given x will beat that function also. Do you see?
Yeah, I get it.
Okay, so that is the whole point of this discussion, is to just say if you know the distribution, you can beat any classifier in the world. You just have to compute this quantity. That's all. That's the point.
Okay, sir.
Okay, so this is kind of reminiscent of our posterior, right? When we did Bayes classifier, there also we had a similar result. When we have 0, 1 loss, we just said that you the posterior, whichever is maximum, you report that, right? So something analogous to that. Okay, anyway, we have spent a lot of time on this, so let's move on. Okay, so this is something that you have to do. Okay, it's very important, and it's just a matter of simple calculation. It is there in my lectures, and I think it is there in Bishop also, but you just check this out. All right, so this is about some probabilistic interpretation of regression. Okay, so I wanted to talk about one more aspect. So we saw J of W. Now we are back to the real world where we are trying to do y minus AX transpose y minus AX, right? This is what we want to do. And we saw two approaches. Normal equation approach, where we got, sorry, not AX. What am I writing? AW. Okay, and where A is just 1 x the first data sample x11 to x1d, like that. So this is A, so this is the second data point, third, we write it like this, third data point, and so on. Okay, and then we got W, we got this solution. Analytically we could show that this is A transpose A inverse A transpose y. Y is just a collection of all the vectors y1 to yn. Okay, so this thing we got. The second thing that we did was gradient descent. So here we say, so the gradient step, right? So I'm not writing all the other things, but just the loop will have a statement like this: wk plus 1 is equal to wk plus let's say minus eta times summation xi w transpose xi minus yi. Okay, so this is what we said, I equal to 1 to n. Okay, so I want a volunteer to just help me with something. Can someone? Okay, maybe I'll pull somebody who has been quiet. I'm going to pull generally whoever speaks. Aditya Jain.
Yes, sir.
Yeah. So what is the dimension of W vector?
Same as d cross 1, d plus 1 cross 1.
Yeah, d plus 1 rows cross 1. So this is also d plus 1 cross
Yes,
1.
sir.
Right. And what is eta?
Eta is a step function, so it's step size. So
Step
it is
size. Step
constant.
size. It's a constant. So this is a scalar. Okay. Now
Yes.
what about this quantity? What is it? Is it a scalar or a vector?
It is a vector.
Really?
So let me do W transpose. No, it's a constant.
It's a constant. Okay. And what about this?
It's a vector.
So what is the dimension of this?
D plus 1 cross 1.
Okay. So what is the first entry in this?
1.
Okay. Okay. Thanks, Aditya. All
Yes.
right. Okay. So everybody understands all these steps here, right? So this is just I'm just trying to recollect. So what we are saying is, if there is an error, okay, so if there is a difference here, you try to adjust, like try to add this point. This is very similar to perceptron also, right? Even there also we were adding xi. Here now we are adding a small weight associated with it. This may be just I mean, there could be some underlying theory why it is like this, but I feel like it is just coincidence. Okay, so this is what we saw yesterday. So this was the view of trying to minimize the cost. Okay. So now there is one more probabilistic view which I will present shortly. But before that, I want to talk about one aspect which is called as regularization. Okay, so I don't remember, but in ML course, did I discuss Lagrange interpolation formula with all of you?
Yes, sir.
Okay, okay, good. So there you, if you all remember, right? So when you are given a n data points, something like this, and this is suppose the actual thing that we wanted to learn. There is some noise because of which you got these blue points. And if you use a Lagrange interpolation formula, what you end up getting is a function which passes through all the points, right? Like this. This is what you may get, right? But one thing is for this red curve, what is the data error? What is it
Zero.
going to 0, right? But it has a high high risk, high true risk, right? This will be very high because there is a lot of difference here, right? So basically, if you remember, right, I didn't mention it, but you can learn. So if you wanted to learn a very complicated function, suppose y is a function of x, a single parameter, single data point you wanted to learn. If you want to learn this blue data point, what you need to do is you need to create your x. So your original x will be 1x, right? This will be your original x. What you can do is you can create an x dash, which is 1x, x squared, x cube, x4, and so on, x5. Maybe 5 of them you can create like this. The benefit of this is you can learn very complicated functions, right? Do you understand? Like when you add all these squares and all, you can learn very complicated functions. Okay, but the problem is when you try to learn your linear model with this new set of features, right? So the corresponding linear model here, W would have had two components, W0, W1. Here your W dash will have W0, W1 all the way till W5. Okay, so there will be 6 parameters that you will have to learn. But the problem is there will have lot of fluctuation. Your data error will be 0, but there will be high true risk, right? So if you can look at the data points, you can always use a very simple model. But when you can't look at the points, you may want to have more flexibility. Okay, but we have to be sure that it doesn't overfit data. Okay, so when you are having this kind of a situation where data error is 0 and the risk may be truly high, this is called as overfitting. Okay. Are there any questions so far? Because I was kind of going through this pretty fast. Okay, so now what we are saying is, let us try to use a complicated model, but instead of getting this red curve, I want to be able to learn a curve like this. Can we get something like this, which is not linear, but perhaps it may fit the data better. Can we come up with that kind of a line, even with using high number of features? So that is the goal, and that is where your ridge regression comes in. So which is what I'm going to tell now. Okay, so what we are going to do is that we are going to have J of W as before. It will be y minus AX transpose y minus AX. Okay, but
AW.
hello.
So it's AW.
Yeah. Okay, thank you. Okay, so what we will do is, instead of just trying to minimize this quantity, I will also penalize. So if you choose a very high value of W, there will be an extra cost coming in. Okay, so this is the penalty for using high values of W. Okay, So do you understand like how this will actually make our model a little more adapted to learning lines which don't overfit? Because if you try to learn a line like this which has wavy nature, W will tend to be high and you are going to penalize it. Okay. So this is called
Sir,
as yeah.
how will W be high for the wavy line? Could you please explain?
So for a wavy line, when you have, see, whenever you have a second degree polynomial, it means that it can make one bend. Okay. When you have a third degree, it will have three roots, right? Like this.
Yes, sir.
So when you are having like a wavy line, it just means that the components associated with that is non-zero.
Yes, sir.
Okay, so if I'm punishing you for having these values greater than or equal to 0, it will ensure that I choose lesser values, so the waviness will reduce, right?
Sir, but it is not necessary. Like the coefficient for x square can also reduce, but the coefficient for x cube can remain high, so the waviness can still remain, right?
It can still remain, but it actually turns out that it reduces throughout and it makes the line smoother. It is you can do experiments with that. In fact, that will be one of your assignments. But I see your concern, right? We are not penalizing this fifth degree more than the fourth degree, or more than the third degree, and so on. Yeah, but it actually makes it simpler. Yeah, somebody else has a question. Yeah, so lambda, how lambda is decided is also an important point. We will come to that, Vipin. I will just decide. I'll tell you.
Uh, so
Yeah.
also as Advait proposed, like if we even in these degrees, if we give priority to the initial the other degrees than the other,
Hmm.
if obviously that will make it more complex. But if we have the flexibility and the knowledge and data to do so, that would be much better, right?
It will be. It will be. So actually, when we come to SVM, it has more. I mean, it will address many of these questions. But yeah, you are right. It is true. If you can do this, right? If you can impose different penalties for each of these terms, it will be better. But it will be more difficult to come up with the exact rules. So that is where we use a simple rule like this. And in the data sets that I will give you to experiment with, you will see that this is more than enough. Okay. So any case, let us try to solve this. So when we try to solve this, again we take the derivative. So that will be A transpose AW minus Y plus W, lambda W. Okay. So
Lambda W.
yeah, lambda W, right? Okay,
That there will
so
be a minus sign for
huh?
A transpose.
Uh, there will be a minus
Okay, no,
sign
the minus sign is taken inside. I got it.
taken inside. Oh yeah. Okay. Yeah. You're right. Minus sign is taken inside. I made two errors and it corrected itself. Okay, great. So A transpose A, then we can write it as lambda. Sometimes people write this as delta square W transpose W. Can someone tell me why delta square W transpose W might be preferred? Instead of, see, it's a constant. Instead of calling it lambda, why would I say delta square?
Positive value.
Yeah, very good. That's the reason. So just say that it is positive. Okay. So we can write this as equal to y. So yesterday somebody was asking me that we add delta square I inverse, right? I don't know who it was, but so this is like if A transpose A was not invertible, you can always add some kind of a small deviation and make it invertible, right? So something like that also comes out of ridge regression. Okay. Is this clear? I mean, this is kind of straightforward, nothing to do. Okay. So anyway, yeah. So this is like L2 norm. Okay. So this is like L2 norm of W. Okay. Norm squared of L2 norm squared of W. And if you use this for the regularization you get ridge regression. So instead, suppose if I use JW, if I use JW equal to half y minus AW transpose y minus AW plus delta squared with a norm of L1 norm, I will get what is called as lasso. Okay, so lasso regression, this is so these are called as regularizers. These are called as regularizers. Okay, and if I use norm 1, I will get lasso, and sometimes you use some convex combination of both the losses. So if you use JW equal to half y minus AW transpose y minus AW plus some alpha times norm 2 squared plus 1 minus alpha times or some beta times, I don't know whether it is necessary to sum to 1, but if you use this norm 1 squared, you will get what is called as elastic net. Okay,
Norm 1 squared or just norm 1?
I'm not sure, just check it out. I'm not sure about this. Please check. I'm really not sure. Okay, anyways, when you use norm 2, the advantage is you can get this tractable solution. With norm 1, it is not easy. You'll have to use gradient descent. Okay, so yeah, any case, so these are all the various things. So now coming back to how you choose this lambda. So this is where I was telling we will have to use what is called as cross validation or validation data set. Okay, so there are this again I will explain later in detail, but choice of lambda. So this Vipin was asking, Vipin was asking, but lambda or delta square. So what you will do is your entire training data, you are going to split it into 3 pieces. So maybe 60, 20, 20. How you do is up to you. 60%, 20%, 20%. So this is called as your training. This one is called your validation. And this one is called your test. Okay. So what you will do is you will learn model 1 with the delta square equal to 0.1. You will learn model 2 with delta square equal to 1, 10, 100, like this 4 models you will learn. Delta square equal to delta square. So this is model 4. Okay, so all these things you will learn on this training set data set. This is stage 1. Okay, then you will evaluate on validation set. Okay, so whichever is minimum amongst all of this, that you will then finally use to evaluate on test. So this is the cycle. This is the true machine learning cycle. So this is called as hyperparameter tuning, right? Hyperparameter selection. Vipin, is your doubt clear? Okay. So everyone else is also fine with this, right? So we will discuss this more details later, but for now I want to do something else. Okay, so lot of agenda today because today is the last class. So any case, so far are there any things you want some clarifications on? Everything clear so far?
So that in elastic net it should be without the square.
You checked, okay.
Yes.
Okay, so there is without the square. All right, thank you. So elastic net, is it summing to 1? Alpha plus beta, should it be 1?
No, sir, not necessarily.
Not necessarily. Okay.
But like alpha plus beta, we call it the net regularization constant.
Okay. Alpha plus beta is called as net regularization constant. Okay.
I mean, I just made up the name myself, but alpha plus beta was written something as lambda. So
okay, that's fine. Okay, all right. Okay, so then so there is a couple of things I want to do. Maybe I will focus on things which are required for your next lab assignments first. Okay, so I will be releasing your next lab assignment in couple of days. The submission will be after your mid-sem, okay? And I will also give you a mini project to do. That also the submission will be late, okay? So the next thing I want to talk about is logistic regression. This is the next topic. Very quickly, I will finish in 15 minutes because it is kind of very easy. Okay, so what is logistic regression going to do? What is it? So basically, we saw that you can use linear regression for classification, right? So what is the disadvantage of using linear regression for classification? I mean, yesterday we saw. Yeah. So the outlier problem, right? So when you try to have this kind of a problem, so this is your y and this is your x, right? Linear regression will do well if the points are not very drastically there, but if there are points which are somewhere here, right? So you will end up learning a line which is kind of meaningless. So it will try to do something like this, right? So so it is going to cause a lot of fluctuation. So using linear regression for classification is a problem. Okay, so what is again I'm asking you some open-ended questions. I don't expect you to answer, but what is the main issue of using linear regression for classification? So this is let me be very clear, this is linear regression for classification. Yeah, what is the main problem here?
So the cost function measures the distance from these points, and
yes, that is correct. But I would say, that all these things are problems, but mainly what I was thinking is like W transpose X goes from minus infinity to infinity, whereas Y is fixed between, it is either 0 or 1. At best, we should be okay with 0, 1, right? Why should we have something that goes from minus infinity to infinity? Do you see?
Yes,
So we shouldn't be using a model which is having this kind of a flexibility when our goal is to just learn parameters like this, right? So this is where logistic function comes to play. Okay, so let me just define what is a logistic function. So sigma of z is called as the logistic function. It has the property this. So we are modeling it as 1 over 1 plus e power minus z. Okay, so this is the logistic function. So how does it look? So when z is equal to minus infinity, okay, so this becomes close to, denominator becomes close to infinity. So this whole quantity goes to 0. Okay, and when z is equal to plus infinity, okay, this becomes e power minus infinity, which is close to 0. So this becomes 1. Okay, so basically we have a function like this. Okay, and this point where it crosses, what is it? Yeah, can someone tell me?
1/2.
Yeah, 1/2, but this is when z equal to 0. And this point is half. Okay, so this is the logistic function. So what we will do, instead of trying to use W transpose X, what we will do is we will use a hypothesis which is sigma of W transpose X. Okay, so this is called as a logistic function, and there are two variants of it. Okay, so let me show you the first variant. So what we are saying is J of W here will be equal to half summation sigma of W transpose Xi minus Yi squared, I going from 1 to n. So this is one variant. What I am saying is I try to find out, like, this function now by design is between 0 and 1. I try to find out which W can I learn a W such that this is minimized. Okay, so this is variant 1. So there are a couple of problems with this variant. Okay, so one is J is not convex. Okay, secondly, it's not a major problem, but no analytic solution. So instead of this, what we will use for logistic regression is, so this is logistic regression with the LMS loss. Okay, so this is called as logistic regression with LMS loss. So what we will use is variant 2, which is logistic regression with cross entropy loss. So what we will do, instead of trying to minimize the cost, we will look at it in terms of probability. Okay, so we will treat this W transpose Xi as probability, and we will do MLE. So can you quickly tell me what is the likelihood if this is the probability? L of W, what is it going to be? Yes.
Minus log of.
Yeah, tell me, 1 to n. So basically what are we saying? So sigma, so the probability, so what is it that we used to write here? So we used to write Pj and yi equal to j, yij, right? This is what we used to write. I don't know if you remember. Right, so then we take the log and then we used to write. So basically after taking the log, it will be summation over I equal to 1 to n. So yij is your data point, whether it is 1 or 0. So yij, yij, now yij, instead of taking 2, since there are only 0 and 1, yi will be either 1 or 0. So if it is 1, the corresponding pj will be
Sigma W.
yes, corresponding pj will be this. If it is yi is 0, then this term will
1
be,
minus.
yeah. Okay, so this is the likelihood, and should we be maximizing it or minimizing it?
Maximize.
Yeah, so you have to be maximizing it, and I will leave it as a homework for you to derive the steps. Okay, derive the rest of the steps. So if you have any conceptual doubts, you can ask, but this is just easy, right? You have to take the derivative, set it to 0, and then get the gradient, right? So you want to, instead of trying to do gradient descent, you should do gradient ascent, because you want to increase the likelihood. Okay, that's the only difference. So you have to use gradient ascent. Okay, and the advantages of this particular cross entropy loss is that this function is actually provably convex. Okay, so it has a maxima, or is it maxima means concave? Yeah, sorry, this is provably concave, so it has a maxima and you can get that, and that is going to be our final thing. Okay, so if you actually deploy this, like if you are given data set like this, if you deploy this particular thing, you will get a suppression like this, and this will be something that you will try out in your homework. Okay, so yeah, so these are the two things. So I will give you one more homework because I couldn't do it. So there will be 2 more homeworks for you, and I don't want to take extra classes and just bore you. So homework 1 and homework 2, and we will stop. Homework 1 is so you had this we had this case where you looked at j of w equal to y minus aw transpose y minus aw, right? We did this and we minimized. This was the cost view. There is another alternate view where you look at like this, like you assume that y is going to be normally distributed with mean w transpose x and with variance sigma squared I. Okay, so all the data points are assumed to have this distribution, and again you can do MLE for w. Okay, when you do MLE for w, you will again get, okay, you will recover uh, this LMS regression. You will get that back. So this is homework 1. So you can stay back and ask if you have any questions related to this. Okay, so homework 2 is y is assumed to be normally distributed with mean W transpose X plus sigma squared I, but W is also assumed to be normally distributed with mean 0 and variance alpha squared I. Okay, so this is we are assuming this, that W is also having this. So if you try to do a map estimate here, if you do a map estimate here, you will recover ridge regression. Okay, so these things are available in my previous year YouTube videos, but I just wanted to finish this for you before the midsem, because you are going to have assignments here. This is part of your midsem, so if you are not able to solve any of this, you can look at last year's videos. If that is also not clear, you ask me, I will help you. Okay, so these things are for you to do. Yeah, so I kind of had to rush because of this being the last class before midterm. Okay, so let's just stop here. So if you have any questions you want to discuss, we will do that now. Okay, so let's stop here. So thanks everyone.
So what is the format for
Yeah,
coding?
so Advay, I'm not planning to ask coding questions for you, because there is a separate lab component. So yeah, so that is one thing. Everyone who is here still, I just want to say, your lab exams only will test theory. So if you don't do too well, don't be worried. Machine learning is not just theory. There is a lab component. So if you are good in lab, that is also good. So that might be enough for you. Okay, so but this theory will make it a little difficult, so it's not always easy to do this well, right?